Hi everyone, today we'll be talking about designing and programming a pen holder for robot illustration. We're team, if you get a bigger bed, you have more bedroom but less bedroom. I'm Nidhi.
I'm Kevin.
I am Elijah.
I'm Garrett.
And I'm Charles Weber. We are all engineers in training, so here's our presentation.
Yeah, so first we'll be talking about the purpose of our presentation, which is mainly to illustrate our process that led to the final design. We will also present the final drawing and the programming that led to the current design, highlight the run-through of the entire project, and then understand the societal impacts of the robot-driven design. Next, Garrett will be talking about our goals.
So our goal for the final project, Project 5, is to use a pen holder that we designed, 3D print it using Cura, assemble it, and use it to draw a picture that we program using RobotStudio. We formulated some goals. For the pen holder, we want to use 2 Sharpies simultaneously, keep them in contact with the workspace, minimize extraneous movement, and of course we want to attach it to the robot itself. As far as the programming goes, we want to draw our intended image and fully utilize both pens. And here's Kevin with the agenda.
So this is our agenda today for our presentation. So first, we'll show us running the program and the final report. We'll talk about the constraints with the pen holder design, the final pen holder design, the drawing selection and programming the drawing, iterative improvements and future improvements to our design, the timeline of the project, the social impact of robot painting, and then conclusion and final remarks. So next, we'll show a video of the project being run. As you can see here, our pen holder holds 2 pens and makes sure that the 2 pens are always in contact with the workspace. Here, the ABB robot is running a program that we coded in RobotStudio to create our final drawing design. If you look closely, you can see that the pen is like drawing like red, but you can also see a slight like blue color with the drawing as well, which is intended and makes the design like looks cooler. So. Additionally, this video is run like at real time. So this entire program took about 1 minute and 30 seconds. So yeah, that's the run through of our project. So next, we'll go through pen holder selection and we'll have Nidhi talk about the constraints.
The first constraint that we had to work with was our budget, which was under $20, not including filament cost, which was provided for us. So the 2 pens that we had to choose under $20 were 2 Sharpie pens. Secondly, our time frame had to be within 2 weeks, so we had to design the part within 2 weeks. Thirdly, we had to account for material constraints such as availability and strength, as we only had PLA available to us. And finally, we must be conscious that the minimum structure width is 0.9 millimeters. Next, Garrett will be talking about our final design.
So we took advantage of the additive manufacturing tools available to us and 3D printed a single part pen holder. The figure on the right depicts its final iteration. Previous versions consisted of up to 16 parts and required 3 times the time to complete printing. Here are some of the features on the left. It can use 2 pens simultaneously, and it boasts rigidity thanks to its single-part design. The linkages connecting the pen sleeves to the body form a compliant structure that reliably restricts unintended lateral movement, especially compared to previous spring-integrated designs. And lastly, set screws offer an optional measure to prevent the pens from slipping in the sleeves themselves. And on the next slide, we can see the pen holder features flexible internal mechanisms that compress under stress and divert structural strain away from the Sharpies. And underneath that, as highlighted in the video, the dual pen functionality allows for multicolor lines on the subject of creative advantages. And here's Charles talking about the 3D printing process.
So an important portion of the manufacturing process comes into play after the part has already been designed, and that is the 3D printing process. When using a slicer program such as Cura, settings such as infill or line thickness all impact the part to a great degree. For our design, an infill of 30% and a cubic pattern was used. This pattern resists movement in all directions while remaining lightweight, and tree supports adhere less to the inside of the print, and they are therefore easier to remove, so they were chosen for the task of supporting the inside of the pen sleeves. Finally, support blockers are used to prevent any support from being printed in the M3 screw holes, which was a previous issue, where the support was generated within the very small hole, making it nearly impossible to remove. On the right, a photo of the model in Cura can be seen alongside its print settings, which in this case were 0.15 millimeters, allowing for high detail while still remaining relatively low in print time, and the aforementioned 30% infill with a cubic pattern. So we will now move on to the inspiration for the drawing with Garrett.
So we took inspiration from geometric designs such as these present on the left. They managed to be aesthetically pleasing while consisting of uniform and repeatable patterns. While our pen holder is somewhat complex, we aim to keep the final drawing design sufficiently simple to maximize efficiency in both development and performance. On the next slide, you'll see the Tesseract design that we chose as a group, keeping these design principles in mind. It consists of two identical cubes scaled about a mutual center, connected by their corresponding corners. The balance between minimalism and complexity results in an interesting and unique image. Moreover, the Tesseract leaves plenty of room on the canvas to showcase the dual pen effect. And the next subject that we'll cover is programming the drawing with Elijah.
Of course. So the first step in creating our code was to ensure that it worked properly. And we did that via simulation in RobotStudio in order to ensure that we would not run into any problems when we actually implemented it in the lab. So we did this by taking the picture that we wanted to design and then overlaying a system of coordinates and converting the coordinates to millimeters, scaling it down to produce a correct drawing, and then figuring out paths manually to trace the different elements of the Tesseract cube. And so the figure below that we have demonstrates a rough kind of path outline simulation that we were able to do and kind of get it successfully working before we actually brought it into the lab. So next, I will be discussing some of the issues that we ran into over the course of this project. One of the first issues that we ran into was developing code. Our initial goal was to design a much more complex image using automatic code instruction generation. However, the code failed to provide the image coordinates correctly, and there was not as much success, and the program was very buggy. So while this would have theoretically been a good implementation under different circumstances, due to our time constraints, we did not have time to properly implement this. So the paths and coordinates and commands in RobotStudio code were written by hand. And next, discussing some challenges with our initial design, we will have Charles.
So if manufactured through traditional methods, our initial design could have been effective, though it required stringent tolerances for proper functionality. And given that we were using additive manufacturing, that offers its own constraints and benefits for our design. So using many connecting parts results in a need for low tolerances, which is a weak point of 3D printers, as they only can be so accurate. And further, the design would have taken many hours for troubleshooting and printing to reach completion, which would have involved many iterations of perhaps hole checking and sizing of the parts so that they fit together properly. And therefore, it was evident that simpler designs were needed. As you can see on the right, there is an example of our early complex design, which contained approximately 16 parts and many different portions that could easily snap off or break if used improperly. This brings us to the solution, which was the complete redesign of the pen holder. Using a one-part design and the ability to print compliant mechanisms, as afforded through additive manufacturing, most issues were addressed. The use of PLA was not perfect for flexible joints, but within a relatively large range of motion, the flex afforded by the design would be sufficient. Also, it was decided that a skeletonized frame would increase strength and decrease mass, as the walls of the 3D print are often stronger than simple infill. So on the right, you can see an example of the current iteration with a recessed flange adapter, skeletonized frame, and the three parallel linkages on each side, flexible linkages. So one of the other problems we faced was pen sleeve slippage. While the press fit of the Sharpie using friction to hold the pen in place would have functioned, the exact size of the hole would have had to be perfected. Then, even with the correct sizing, deformation over time would decrease the grip on the Sharpie. So an M3 set screw and M3 nut were selected to contain the pen within the sleeve, applying pressure to the outer side of the pen. After adding an insert hole for the nut and a hole for the M3 screw to pass through, a nut could be added post-print. This design choice prevents any movement, and the pressure on the pen can be adjusted as necessary, thus also making it more adjustable in terms of the length of the Sharpie within the hole. So it was an overall improvement and also better strengthens the design for continuous use. So now we'll go to Elijah to explain the recommended future improvements.
Yes, so some of the recommended improvements we have are mainly for efficiency and streamlining the workflow. The first of which would be to select the intended drawing or design style before actually creating the tool model. This will allow for a simpler design without the loss of functionality and will greatly improve the time process. Additionally, we recommend that you design the tool in a flange downward position, meaning that the tool is aligned correctly with the plane of the robot, which will make calibration much simpler and less motion to account for. In terms of printing and creation of the part, we also recommend dual extrusion printing, which will allow for more flexible mechanisms and a more flexible and pressure resistant part, such as using the material TPU. We also recommend that if you were to use the automatic code generation method to begin to develop that code parallel to the development of the toolpath in order to better streamline that process and create more complex designs as you wish. And next, I will be discussing our project schedule, which we designed through the use of a Gantt chart. And as you can see, we were able to stay very much on schedule. While we did go over time with the 3D printing process in the part of the pen holder, ultimately we were able to make up that time, successfully complete the lab, and are currently on track to finish the presentation and report on time. Next, discussing the social impact, we have Kevin.
So now we'll be talking about the societal impacts of robot painting. So one societal impact of robot painting is the significant decrease in the amount of time it takes to complete one piece of art. Another potential societal impact to come from this project is the possibility of aiding artists with disabilities in order to allow them more opportunities to express their artistic talent and experiment with these new tools at their disposal. With access to such technology, artists can continue to materialize their creative ideas while minimizing the amount of time and labor spent on producing them. However, one caveat of this increased efficiency is that the quality of art may be decreased. There may also be the unintended side effect of decreasing the value of handmade art should the robotic art prove to be good enough of a substitute for the general art market. This is addressed in our proposed study, where the subjective comparative quality of art will be analyzed through the lens of the consumers. So next, we'll be going over the study that we plan to implement. The specific population that will be included in this study will be customers of a group of artists that regularly create and sell paintings. Our key question for this study will be, can customers tell the difference between a handmade painting and one made by a robot? Our hypothesis is that customers will be able to notice slight imperfections in the handmade art that will make the answer obvious for them. This study will be considered both quantitative and qualitative, as in the end, our data will show how many customers are able to identify the handmade painting, as well as their method of going about it. This will be a cross-sectional study, as each customer will only participate in the study at one point in time. Our method of data collection will be a survey asking customers to identify which painting that they think was handmade, and a question asking, how did you determine who painted this? 3 demographic characteristics we would like to know about our participants are age, gender, and level of education. 2 measures that we will use in our study are participants' answers to their survey, as well as observation of the methods they use in identifying which painting was which. We expect to observe the participants analyzing the brushstrokes and see if they are very similar or repetitive. So now we'll go over conclusion and final reflections with Elijah.
So ultimately, although we ran into some challenges, the project was successful and we were able to complete the vision that we had. This project is a very strong combination of technical literacy in terms of understanding the robot, being able to operate it, being able to implement code, and the artistic vision in terms of creating the design and having an artistic vision for what the robot is meant to create. And so we believe that we proved with this idea that it can be implemented on a larger scale, especially with more time, funding, and could be taken to a professional level as well. However, we do believe that timeline planning and specialization and laying out the time frame is a very important element to deliver proper final results. And so during this presentation, we have talked about our process in designing the current pen holder, programming the robot, and creating this drawing. And while there may be delays, ultimately we are confident that we're able to finish the final report and bring this conclusion to you all. So thank you for listening. And do you have any questions for us?